Hello everyone, let's continue with the cell leakage power, which is the last in the intrinsic leakage power group, and then we can move on to the gate leakage power. So cell leakage power is nothing very related to the leakage power. It's an average of all the powers that you see for that particular pin. So for example, let's take an example over here. Okay, so let's say you have a AND gate over here, and an AND gate has got 4 different states, and the different states can be referred using a table. So if you refer to a truth table of this particular AND gate, you have you have A B, and you have 0 0 0 1 1 0 1 1 and 4 different states over here. So for the state called as 0 0, the output will be 0. For the state 0 1, the output is 0, and so on. So this is the different states, and this can be converted in a library format. The states can be converted into a library format which looks something like this. So it will be called as a not of A and not of B, not of A and B, A and not of B, and A and B. So these are the 4 different states which are corresponding to the truth table that you see over here. Now each and every state will have some amount of leakage power. So let me show you that. So if you say, for example, cell is called my AND, and the leakage power whenever your state is not A and not B, for example this state, the leakage power is a value called as 0.0082 microwatts, which is 0.82 nanowatts, and so on. So remember in the last video we have shown you the leakage power unit section in the cell section. So the units referred to, we can refer to the units from that particular video. So let's say this leakage power when the state is not A and not B, it's about 0.00082 microwatts. The leakage power when the state is not A and B, which is the second state, the leakage power is, let's say, 0.01127 microwatts. And similarly we will go with the other states. For example, the whenever your state is A and not B, for example this one, whenever your state is A and not B, the value not B, the value is 0.03313 microwatts. And similarly the leakage power when your state is A and B, the leakage power is 0.36651. So you have so this same cell has got 4 different leakage powers. So 4 different leakage powers. So in order to calculate the cell leakage power, it's just the average of all of them. So you add all of them, you divide it by 4, and this is the value that you get. So cell leakage power will be the average of the all leakage power that you see in this particular group. So the average leakage power of this particular AND gate will be 0.1029325 microwatts. Okay, so that's what the in a cell leakage power is actually meant. So this is just the average of all the leakage powers. Next, so this brings to an end to the intrinsic leakage power group. One point to remember over here is that the cell leakage power has to be positive. It can't be negative, because the values over here, the values of the power are all positive. So the leakage power has to be positive. If for some reasons if you see a negative value over here, it means there is some problem with the library. So cell leakage power has to be positive. Okay, so that was about the last group in the intrinsic leakage power section. We have one more group. Remember we talked about the tunneling current, and that comes into the gate leakage power group. So there is a different way, there is a very interesting way to measure the gate leakage power. Let me show you that. So if you look into the gate leakage power, it also comes under the leakage current section. So before that, let me show you how do we measure it. So for example, gate underscore leakage, it's a CCS power format, and let's say you have an inverter connected back to back. So this is just a setup or the characterization setup to measure the gate leakage current. Okay, so let's say you have this particular inverter which is driving this particular inverter, and this inverter needs to be characterized. So we should put it in a reverse way. If you want to characterize this particular inverter, it should be driven by another inverter, another similar inverter, or any kind of inverter. So it needs to be driven by something. Okay, so in that case, whenever you want to characterize this particular inverter in form of its gate leakage power, or if you want to measure the gate leakage power of this particular inverter, it will look something like this. So if you look into the leakage current, this is the syntax of the gate leakage. It comes under the leakage underscore current group, and the way to mention it is something like this. So if you need to mention the state over here. So when A is not the gate leakage of Z we are trying to measure, so it basically says that your leakage current flows whenever your A is inverted and the input low value. So whenever you say the input low value and input high value, there are 2 different values of the gate leakage that needs to be filled over here. Okay, so let me try to explain you each and every one of them over here. So let's try to expand the inverters over here. If you try to open up the inverters over here, you have this particular PMOS and NMOS for both the inverters. Now whenever you say as input low value basically specifies that if your input A is equal to 0. Now if your input A is equal to 0, it means that your input which is at the previous inverter over at this particular point has to be at logic 1, because if it is a logic 1, then only this line will go at logic 0 and your A will receive a logic 0. Now under this particular condition, when you see your input A equal to 0, your PMOS will be turned on. Okay, your NMOS is off, your PMOS will be on, and because of this one, because of the logic 1 at the input of this particular inverter, your NMOS is on. So there will be the direction of the flow of the current will be something like this, and this current flows from the power pin of this particular inverter through the gate pin, through this particular line, and to the ground pin through this particular NMOS transistor. So your flow of the current is going from the cell and it goes out of the cell. So any current that enters inside the cell, that is being treated as positive, and any current that goes outside the cell, that is being treated as negative. So in this case, because of the convention that we follow for measuring the current, since this particular current is the value of the current that flows outside of the cell through the gate, it is called as the input low value as a negative value. Okay, so this current value will be a negative value because it flows outside of the cell. And similarly, if you look into the next condition, which is input high value equal to, which is for the input underscore high underscore value, it basically tells us, it basically asks us to measure the current or the gate leakage current at this particular point whenever your input is high. So when your input is high, A is equal to 1. If A is equal to 1, the previous input has to be equal to 0, and when this is 0, this becomes this transistor turns on. When A is 1, this transistor turns on. So there is a flow of current from the power pin of the driver through the PMOS transistor through the gate of the NMOS, and then it enters into the ground. So in this case, the current is entering into the cell that needs to be characterized. In the previous case, the current was leaving the cell that needs to be characterized. So in this case, the current is entering from the power pin of the driver through the gate of the NMOS transistor into this particular cell. So following the normal convention of current, in this case the current has to be positive. So any current that leaves the cell, that has to be treated as negative, and any current that enters the cell, that has to be treated as positive. And that's what the convention that is being followed across the characterization tool, and this is what it does. So as a result of that, the input high value, the leakage current or the gate leakage current for the input high value is 0.4, which is a positive. Okay, so that was about the gate leakage current, and this is how, if you want to characterize this particular cell, or if you want to open up the library, the power library for this particular cell, and find out what is the gate leakage current or the leakage current for the gate, this is how the values will look like. All your low values will be looking as negative 0.2, the high value will look at 0.4. So basically the point is, the current which is entering the cell, it is basically treated as positive, and the current which is leaving the cell will be treated as negative. It is just the direction of the current, nothing else. Okay, so these are the values of your gate leakage current, and that brings us to an end to the static power concept. The next topic that we are going to start is the same power characterization, but it will be dynamic power, or the switching power, or hidden power, or the internal power. So this kind of power, what happens whenever your inputs are switching, or whenever there is some activity inside your cell, that kind of power is referred to as dynamic power. In the previous case, all the power leakage, or the leakage was all happening, or the power dissipation was happening whenever your inputs were static. Okay, there was no switching activity happening. So in this case, now we are trying to evaluate the power when your inputs are switching and when there is some activity happening inside your cell. So let's start with the dynamic power characterization from the next video. Thank you.